Sharjah, which is one of the Emirates, United Arab Emirates, and we're going to have two huge telescopes over there as well. So we're really looking forward to that, because that's going to help members, certainly on the east coast of the US and also in Western Europe as well, because those telescopes will come on slightly earlier. So it's really easy to use SLU. You control the telescopes, but what makes SLU really different is that you can watch what everybody else is controlling the telescope to view. So we always think of it a little bit like a jukebox, that one person is controlling the telescope, but everybody's watching the live views. And that our community of members is global. It's absolutely huge. But not only is it huge, but the variety of people's interest. Some are just space enthusiasts. They would watch a TV documentary about space or astronomy, and they love just collecting images maybe from the live telescope feeds. But we've also got advanced amateur astronomers who do art astronomy, which is creating beautiful, beautiful astrophotographs from SLU's telescopes, all the data that they gather up. We've also got a bunch who love doing a load of science. They track asteroids and comets, and I think they've made nearly 10,000 submissions to the Minor Planet Center because they've been monitoring near-Earth asteroids, these asteroids which pose a potential risk to Earth. So, there's a whole gamut, and it doesn't matter if you're absolutely brand new or if you own your own telescope or you're an advanced astronomer. There's a place for you to find your own little corner of our community. So if this is the first time you've found SLU, then come along, join the community. You will not be disappointed. And don't forget, every day you'll be able to see the fabulous views through SLU's solar telescope, which is also at the Institute of Astrophysics of the Canary Islands. But anyway, let's get back to today's event, this annular eclipse. Now, the annular phase has already finished in the Middle East, so we're seeing the moon, the black silhouette of the moon, slowly leave the sun. But that shadow is racing across the Indian Ocean, Indonesia, and is going to hit Singapore. Now, if we take a quick look at the Singapore feed, we'll see that there the moon is slowly encroaching on the sun, further and further and further. So there we go. As we watch this feed, more and more of the sun is going to be covered. So Bob Berman, he disappeared on me, but let's welcome back SLU astronomer. He's an incredible author. He wrote The Sun's Heartbeat. If you're interested in the sun, and if you're watching this, you probably are, read Bob's book called The Sun's Heartbeat. And Bob, you also write for Astronomy Magazine and the Old Farmer's Almanac. Is that correct?
Yep, quite right. I'm the astronomy editor of the Old Farmer's Almanac. I have been for, more than a quarter century
Too many
now.
years.
And I'm a contributing editor and a long-time columnist with Astronomy Magazine. I was with Discover for 17 years before that. So all of this stuff is really kind of a monument to inertia.
And a lot of amateur astronomers will know you probably from your column in Astronomy Magazine.
That's right. Despite the fact that I'm just making all of this up as I go along.
Never. But you also run the Strange Universe Club at SLU, and we're going to be getting you back to doing your weekly audio shows where you're commentating on whatever members are controlling the telescopes to see, but also if members can listen to you every night, because you've recorded some audio descriptions of some of the most popular objects in the SLU 1000 catalogue. So people are listening to your wonderful dulcet tones and your audio descriptions when they're watching the live feeds coming in through the SLU's telescope. But anyway, Bob, back to the sun, our subject at hand. And you were talking earlier about seeing different layers of the sun. I think you mentioned the photosphere and the chromosphere, and you mentioned several components and features. What more can you tell us on this subject about our local stars?
Oh, yeah,
I think sometimes we forget.
Yes, because obviously we only see the surface. We don't have X-ray vision, and starting in 1610, we had the benefit of telescopes looking at the surface, so we could see spots and spicules and granulation and faculae, as they're called. We see prominences on the edge during total eclipses, and the beautiful lacy patterns of the solar atmosphere called the corona. But what's causing it, what's underneath? And it's only in more recent years that we've had new techniques like helioseismology that measures the pulsations of the sun, because the sun is like a giant subwoofer. Its surface rapidly pulses up and down, and the way it moves tells us about what's underneath, just as the way the earth moves tells us about earthquake, not just formation, but also propagation through the earth. So through all of this, we've learned, and to me, the most fascinating thing, of course, is where does all that heat and light come from? And that's the solar core. So I want everyone to picture that if you could see the sun in the sky, not the place where it's giving off the light. That's what we're looking at. That's this yellow thing. That's the part that radiates all of the light and the heat. It's a very thin layer. It's only about 200 miles thick. So picture it just almost painted on, like a shellac. Very, very, very thin layer is letting out the light and the heat. Where it's coming from is a spot in the center. It's only less than a 20th the size of the sun itself, called the core. And in the solar core, listen to this. There's the energy of 96 billion 1 megaton hydrogen bombs released every second. Every second, there's the power of 96 billion H-bombs going off. And all of this unimaginable power radiates and tries to escape. Has a hard time doing so because all of the bits of energy and even some solid particles, including particles that don't get stopped by anything called neutrinos, as they're racing out, they encounter more solar stuff, because the sun weighs a lot. Weighs the same as 333,000 Earths. So it takes a while before all of that reaches the photosphere, and that's where it actually gets released. So that's the thing that we see. So there's a lot going on under the surface, including apparently a conveyor belt that carries material from the equator poleward and in a kind of circular fashion, and the sunspots we see are just manifestations of that. So a lot is going on.
So Bob, you talked about some of these particles, and let's think about a photon being generated at the core of the sun. Aren't there some amazing statistics about how long its journey takes to actually reach that thin veneer that you're talking about? 200
yes, and
miles on the surface of the sun.
You'll see different figures, Paul. A photon itself gets to the photosphere and gets released fairly quickly, but for other bits of material to squirm its way to the surface, you'll read 50,000 years, you'll read 1,000 years, you'll read several months. I found that the literature is so discordant about how long it really takes material to get from the core to the surface that I don't actually trust any of it, which is why I didn't quote anything. So it takes, let's put it this way, it probably takes a while because there's a lot there. As I said, the sun weighs the same as 333,000 Earths, or I think to put a figure on it, 10 to the something like 33 power grams. So it's a hefty ball we've got there in the center of the solar system.
So however long this poor little photon takes to reach from the core where it's being generated to the surface is a long time. We don't know specifically how, but it's maybe thousands of years, whatever. But once it's released from the sun's pressure and gravity, it doesn't take long to then reach us, which is what these are doing now. 8.5 minutes. So we're seeing the sun at the moment as it was 8.5 minutes ago. Is that right?
That's right. And
so it's a little bit like a time machine.
So we don't have bad seats for the show. It's not like we're so far up in the balcony that we're seeing old news because it doesn't change very much. I should also mention a new layer of the sun between the core and the photosphere that we've recently discovered called the tachocline. And that's a boundary about 7/8 of the way from the sun's core to the edge. And at that boundary, the sun changes from rotating almost like a solid ball, which it does from the core all the way to almost the surface. And then there's the outer 1/7 of the sun or so, where everything is chaotic, where the sun rotates at a much faster speed. It takes only about 25 days to rotate. The poles take closer to 30 days. All of this looks like it takes a few days longer because we're going around the sun in the same direction it's rotating. So from our perspective, it looks like sunspots take not 25 days, but more like 28 to go around the equator, and more like 35 to go around the poles. But that's because we're moving along in the same direction that the sun is spinning. So that gives us a false sense of how long it takes the sun to rotate.
We're so familiar with the sun. It sounds almost cliche to say that, but this orb in the sky that we see every day, we're fortunate enough to have special telescopes that we can look at it in these wavelengths that we've been talking about. It's quite easy to forget, though, Bob, that the sun is a star, our local star. So how does it measure up in comparison to other stars that we've studied? Is it particularly special? Is it run-of-the-mill? Is it
No,
big,
it's pretty average. It's pretty average. Most stars are lighter weight than the sun and dimmer than the sun. So the sun is a little bit brighter than average. Only about 13% of the stars in our galaxy are like the sun. We say spectral class G. That indicates a white star. The sun is really pure white. I know some textbooks say that it's yellow. And from the surface of Earth here, look at the photograph. It certainly has a lemony yellow appearance. But in truth, it's a white star. Astronauts and high-altitude balloonists, they all report that the sun is as white as snow. So why does it look yellow? It's interesting. This is fascinating. This may be the most fascinating fact. As the sunlight comes off the photosphere, and it consists of all the colors of the rainbow, as it tries to get to us, it has to pass through our air. And the quality of our atmosphere is such, the size of our air's atoms and molecules are such, that the shorter wavelengths of light, the blue, get scattered, get bounced in all sorts of different directions, 6 times more readily than the red does. So because of that, we have a sky that looks blue. We get the blue sky, not for free. That blue light had to come from somewhere. So that blue light that gives us the blue sky was robbed, subtracted from the sun's light that was en route to us. So what we see when we look at the sun, like now in this image, or any day that we look up at it, is the sun missing a bunch of its blue light that went into giving us the blue sky. Another way of saying that is that the green and the red part of the spectrum, there's only 3 primary colors of light, red, blue, and green. So with the blue scattered out, we have an abundance, an overabundance of red and green. And it's a fact that red and green light, when combined, produce yellow. So the sun appears yellow because there's an extra red and green coming to our eyes because the blue is missing because it's been taken out to give us our blue sky. So because of that, we have an appearance of a yellow star. But as astronauts tell us, the sun above our atmosphere, the true color of our star, the sun, is really as white as snow. And you can prove that now that it's winter time in the northern hemisphere. The next time you have a snowy day, I'm urging everyone to just look at the snow on a clear day when there are no clouds in the sky. And you'll notice something amazing. The snow is lit up by the sun hitting it, the slightly yellowish sun, but the snow is also being illuminated by the blue sky. So what happens is that those colors recombine. The blue that originally was part of the sun but now went into giving us our blue sky bounces off the snow. And the yellowish sun made of primarily the red and green light, that's all that was left of the sunlight, bounces off the snow. Those two colors recombine to restore the original colors of the sun. And so what I'm telling you is that the color of snow on a clear day is the true color of the sun that astronauts see.
Okay. So I love that fact, Bob. I had some new lenses put in, actually, to my eyes. And what I noticed there was they only do one eye at a time. And my white coffee mug, through the eye that hadn't been done, looked slightly yellow, slightly creamy. But through the new lens, was totally white. So I'm sure things kind of change for individuals as well. But I totally white. So I'm sure things kind of change for individuals as well.
In your new eye, you're seeing the blue of the sky, much more richer blue, aren't you?
Everything is a lot